that we have two power series, bk, k going from 0 to infinity, x minus a, centered at a, and another one, k going from 0 to infinity, ck x minus a at the same center. And suppose these two things are the same as functions of x on the interval I. Of course, that interval includes the center a, and to the left, doesn't matter how small this interval is around a, and there are this infinitely many x value that you tried it here. For that fixed value of bk and ck, this infinite series always turns out the same. And what is it you want to conclude about these two infinite series? Is bk and ck is exactly equal for all the k's, all k's from 0 to 1 and 2 and things like that. If it stopped not going to the infinity, if it stops at n and n there, that is not going to be an infinite series, right? This is going to be a polynomial. If two polynomials, if you plug in x values, many things, if they all agree the values, same values, then those two polynomials has exactly the same coefficients. You will probably believe that. Actually, proving that is actually tricky if you think about it. An infinite series is even harder. But here's the thing. Here's how the proof, kind of outline of the proof, is very rough proof, but I think it's something you can fill in later on. These two things are the function, is a power series defined on that interval I, right? So I'm going to call that f of x, the first power series function, k going from 0 to infinity. Second, I'm going to call different function. It looks different, and you go through a different algorithm and potentially different coefficient. And they're all a convergent series on I, right? And theorem says if there's an open interval, their derivative is defined. It has the same radius of convergence. If you didn't pay attention to this last part, you can differentiate, and it becomes another infinite series. And if you apply the ratio test, it converges in exactly the same interval. Interval doesn't shrink or is exactly the same interval. So you go ahead and compute in this one in here, differentiate. One time and two times, eventually k times. You can differentiate k many times. It starts from constant term and x to the first. As you differentiate many times, those first terms disappears, right? Constant term, after you differentiate one time, it disappears. So you can write down the formula of a 10th derivative of this one and plug in x equals a there, and plug in x equals a, and plug in x equals a. Because a is the center and you have lots of term x minus a to the k shows up, if you plug in x equals a, it simplifies a lot. Okay? So if you actually do that, what's going to happen is it's going to pick up b1. It's going to pick up b2, 2 factorial. Do you know where the 2 factorial is coming in? As you differentiate this term over and over, k comes down and k minus 1 comes down and k minus 2 comes down. You will pick up 2 factorial eventually. And this one, bk, and you pick up k factorial. So if you actually differentiate this power series k times and plug in x equals a, what survives is the constant term that's surviving after you differentiate k times, and then it looks like this. And g of x, you do the same thing, differentiate it one time, then it's going to be c1, and differentiate it 2 times, and plug in x equals a, then it's going to be c2 times 2 factorial. If you differentiate k times and plug in x equals a, then you're going to pick up ck along with this k factorial multiplied to it. These are the special values of this derivative when you do it separately. But we assume these two functions are the same. Here, as the functions f of x and g of x, and picks up exactly the same value, although potentially they go through potentially different series. So all this derivative, if the functions are the same, derivative must be the same too, right? What can happen? So if the derivative is the same, the values of the derivative must be the same as well. So this proves that b1 is a c1 and b2 is a c2 because this factorial cancels, and bk no matter what, and it's going to be always the same. So you can show that there's no two different versions of the power series. They're unique. Once you write down the power series, there's only one way to do the power series in there. The reason the Taylor series has this kth derivative of A, and it's because of this, it's picking up the structure of a Taylor series coefficient, which is part of the homework problem, right? Yeah. So I'm going to give the nickname for that uniqueness of the coefficients. What I mean by that is just there's an overlying structure of something called a function. No matter what algorithm you go through, there is this function, input and output, and forget about the process. There exists an input and output data in relationship. For that, however you write the power series, and given the same center, the coefficient has no choice. It has to be one thing. Uniqueness of the coefficients. Important to, I bump into this discovery. How do you know that's exactly the coefficient that the other, this one tells you? And whoever does it is going to be exactly the same. So in discovering, functions of a natural phenomenon in a physics problem, this type of uniqueness is an important result to rely on. This is it, and this is actually the function. All right, and then